Hello.
Hello, can you hear me?
Yes, I can hear you.
Maybe we can start now.
Okay.
So hello everyone. So this is LSO pre-LSO session number 4 on linear programming and the simplex method. Today we have our speaker Shubham Kesari. He's a PhD scholar in the Department of Management Science at IIT Kanpur. He's been working with Dr. Avijit Khandra. He's also a Prime Minister's Research Fellow. So let's welcome him. And the floor is yours, Shubham.
Thank you. So, welcome everyone. Today I'm going to talk about a little bit about LP. So, you have already had an introduction on modeling and LP in the first session. And the main focus of this lecture will be on simplex algorithm. We will build upon how the simplex algorithm works and we will borrow ideas from graphical method. Okay, so I am a PhD scholar in the Department of Management Sciences, IIT Kanpur. This is my website and this is my email ID. You can reach out to me anytime. If you have anything, you can contact me. Okay, so before this, whatever we are going to discuss in this section has been borrowed directly or indirectly from a course which I did under my supervisor in IIT Kanpur. Okay, so the objective of today's session is to understand
Shubham, can you unmute yourself? Thank you.
so was
I can hear you now.
Okay. Thank you. So the objective of today's session is to understand the graphical method. Then we will move on to the basic theorems that led to the development of simplex algorithm, and then some theoretical foundations of simplex algorithm. Okay. So this is the content of today's session. We will not go into the details now because we will see as we proceed. Okay. So let us see one simple linear programming problem. So there's a carpenter who has two products, tables and chairs, and he has to fulfill the orders which he is receiving. Um, the, and he is trying to maximize the revenue he is getting when he sells these products. The cost of the revenue from table is 7,000 and the revenue from chair is 4,000, but he has some capacity limitations like timber and labor. So each table requires 5 units of timber and 9 units of labor. Similarly, each chair requires 2 units of timber and 6 units of labor. So we can simply model this very easily. So we will say let X be the quantity of tables produced and Y be the quantity of chairs produced. You see, when I'm saying quantity, so it should be an integer programming, but we are looking at it as a linear program right now. So X and Y are continuous variables. You may argue that it shouldn't be continuous variables, but for the time being, we are considering as continuous variables. So the quantity of timber utilized for producing X tables will be 5X plus 2Y will be the quantity of timber required for producing the chairs, and the availability is 40 units. So this is the first constraint. A similar constraint will be there for labor requirement. The objective is to maximize the revenue. So for each table, the carpenter is getting 7,000. So it is 7x. And for each chair, he is getting 4x. So it is, 4y. So it is 4y. So this is a formulation to this problem. And this is a linear programming formulation. Why this formulation is linear is because the objective function is linear in terms of the decision variables. The constraints are linear and the variables are continuous. So these are the requirements for a, a, a model, mathematical model to qualify as linear programming. So these are the properties of linear program: proportionality. So the constraints and the objective. So the terms in the constraints and the objective. So these are the terms in the constraint and objective. Each term is directly proportional to a decision variable. So if you increase X, if you double X, the quantity will be doubled. So it is linearly proportional. Additivity, it means that the terms in the either in the objective function or in the constraints are connected via plus or minus. Divisibility, it just says that the decision variable should be continuous. If these three, any mathematical model qualifies these three properties, then we will say that it is a linear programming problem. Okay. So this was an introduction to what a linear programming formulation is. Is it all right? Okay. You can unmute yourself anytime and ask questions. Okay. So we will move on to graphical method. So how we will see graphical methods? I have some formulations, and for each formulation we will see how we are solving that problem using graphical method. First of all, to solve a problem using graphical method, you need to have two variables in the linear programming problem. If you have more than two variables, then it is difficult. So for three variables, you can have three-dimensional plot, but beyond that it's not possible. Okay, so we'll see only two variable problem when we are studying graphical method. So this is the first LP. So what we'll do is we will draw the constraints and determine the feasible region. Okay, we will see what points satisfy these constraints and we will draw the feasible region, and then we will draw something known as ISO cost or ISO profit line. We will see what these are. So this is the formulation, and I have drawn the feasible region for you. So this is first constraint, this is the second constraint, and this is the third constraint. So I have marked the three constraints, and this shaded region is the feasible region. Okay. Now what we will do is this objective function, it is an expression. We will make this an equation. So what we will do is we will say 2x minus y is equals to alpha, and we'll see what that line is. So suppose at any point, so suppose at 1 comma 1 by 4. So when you say 1 comma 1 by 4, we will see what is the value of the objective function. It becomes 2 minus 1 by 4, which is 7 by 4. Okay, and we will draw this line. So suppose this is the line. It may not be appropriate because I am just drawing it by hand. So suppose this is the line. Now what we'll do is, so this line is known as the ISO cost line. Why? Because the value of the objective function does not change if you move along the line. So every point in this line has an objective function value. Every feasible point in this line has an objective function value of 7 by 4. Now what we'll do is we'll move this line and we'll see on which direction is the value of the objective function changes. So if you see, if you move the ISO cost line in this direction, the objective function value increases. And if you move the this ISO cost line in this direction, the value of the objective function decreases. So this is the region where the objective function value increases, and this is the region where the objective function value decreases. Any point in this region has a higher objective function value as compared to this line we have plotted. So this is a maximization problem. So we'll move that line towards that region where the objective function value increases. And what we'll see is that once we move, we will see that this ISO cost line exits the feasible region via a point, a corner point. And at this point, the objective function is maximum. Okay. So what we observe is at 2 comma 1, at 2 comma 1, the objective function value is maximum, and that is the optimal solution to this problem. Okay, which is a corner point. So we observe that a corner point is optimal. Okay, so this is one observation we have made. We will see another example. So in this case, the constraints are the same. I have just modified the objective function. So I have the same feasible region, and we will again draw the constraint. So in this case, you take any point and you draw the ISO cost or ISO profit line. So once you draw the ISO cost or ISO profit line, you will see it is something like this. Okay, just a minute. It is something like this. All right, and we will see that in this side, the value of the objective function increases, and in this side, the value of the objective function decreases. And it exists this feasible region coinciding with this constraint. Okay, and we observe that at this point, this, I'll change color, at this point, and all the points in between have the same objective function value. Why? Because all the points in this line will have the same value because it is falling on that line, and all the points in this line are optimal. Okay, all the points in this line segment connecting 1 comma 0 and 2 comma 1 are optimal. But what we observe is that there are two corner points in this line and both of them are optimal. So this observation that a corner point is optimal holds true as long as the feasible region is bounded. You see, the feasible region in this LP is bounded, and we are observing again and again that a corner point is optimal. So using this idea, we can have a very simple algorithm to solve this problem, that if your feasible region is bounded, you check the objective function value at the corner points. So first you have to identify all the corner points in your LP. You obtain those points and evaluate the objective function value at each of the point, and whichever point has the best objective function value. Why I'm calling best? Because it can be a minimization problem or a maximization problem. If it is a minimization problem, your objective function value will be minimum. For a maximization problem, it will be maximum, and you pick that point where the objective function value is maximum. Okay. So observation and LP optimal solution is at a corner point. This observation holds true as long as the feasible region is bounded. Okay, this observation is only true when the feasible region is bounded. We will see what happens when the feasible region is unbounded. The isocost line always passes through a corner point when leaving the feasible region. And this algorithm, what is that algorithm? If your feasible region is bounded, you obtain the objective function value at each corner point, and one of those will be optimal. Okay, so this is a simple method of obtaining the optimal solution when your feasible region is bounded. Any questions? Okay, next we have a different LP. We have two constraints and an objective function. This is a two variable LP, so we can use graphical method. What we'll see is that this is the region, this is the feasible region. Okay, this is the feasible region, and we have an unbounded feasible region. Okay, there is no constraint which bounds the feasible region. Now we will do the same thing. We will draw the isocost or isoprofit line. So take any point. Suppose this is the point 1, 1, and we obtain the value. So whatever it is, so it will be 2 minus 1, which is 1. So we will have the equation 2x minus y is equals to 1. We'll plot that line. So suppose this is that line. Okay, let me draw it using red color. So this is that line, and we will again see in which direction there is an improvement. And what we'll observe is in this direction there is an improvement, and in this direction there is a decrease in the objective function value. Since it is a maximization problem, we will move the isocost or isoprofit line in this direction. And what you observe is that it exits the feasible region at 3, 2. And that is the point which is optimal in this case. Although the feasible region is unbounded, the isocost line exits the feasible region via a point which is a corner point. Okay, so what we observe is that the feasible region is not bounded, but when we move in the direction of improvement, the isocost or isoprofit line leaves the feasible region via a corner point. Hence it is optimal. Okay, again we have the same constraints, but I have changed the objective function value. Okay, the same region is there, the feasible region remains the same, but the objective function expression of the objective function changes. Once you plot this, it will be something like this. Sorry, it is x plus y, so it will be something like this. Okay, it will be something like this, and we will see that in this direction the objective function value is increasing, and in this direction the objective function value is decreasing, and we will move it along the direction of improvement. And what you will observe is this isocost or isoprofit line never leaves the feasible region. Therefore, you have no optimal solution in this problem. No optimal solution. That is, your LP is unbounded. Okay. So here the movement towards the direction of improvement never ends. You can move the objective function isocost line more and more, and you will see there is always an improvement, and hence you can improve the objective function indefinitely. Therefore, an optimal solution does not exist. When we say does not exist, it means that the solution is unbounded. In general, if the feasible region is unbounded, so when you have an unbounded feasible region, an optimal solution may or may not exist. Okay, may or may not exist. If it exists, if there is a if there is an optimal solution, it will always be at the corner point. Okay. So this is another method of finding an optimal solution. This is a method of finding an optimal solution when your feasible region is bounded. So the condition is your feasible region should be bounded. This is the first condition. And the second condition is if the optimal solution exists. So in these two cases, a corner point will be optimal. Okay. We will have another last case. So one case is your feasible region is bounded. The other case is your feasible region is unbounded. The third case is when you don't have any feasible region, no feasible solution. Okay. So once we draw these three equations, we will see that this is the side which satisfies this constraint. This is the side which satisfies this constraint, and this is the side which satisfies this constraint. So there is no feasible region in this problem. Therefore, this problem is infeasible. Okay. We will say that this problem is infeasible. So we have seen all the possible cases. Once when the feasible region is bounded, once when the feasible region is unbounded, and once when the feasible region does not exist. And this is exhaustive. We have exhausted all the cases. There are no other cases which can be possible. Okay. So once we have exhausted this, we can come up with an algorithm to solve using graphical method. So whenever you are given a LP, what we have to do is we have to first construct the feasible region. Using each of the constraints, you have to construct the feasible region, and you have to check first whether the problem is infeasible or not. If it is infeasible, then you stop. Okay. So this is an algorithm. Okay. Algorithm of solving LP using graphical method. So what you have to do is in the first step, you have to draw the feasible region. If the feasible region does not exist, then you just stop and say that the problem is infeasible. Okay. But if your feasible region is bounded, second case, what you do is you compare all the corner points. You list down all the corner points, you compare their objective function value, and you declare that corner point to be optimal where the objective function value is the best. Okay. So this is when the feasible region is bounded. When the feasible region is unbounded, you will have two cases. What is the case? First, you have to check whether optimal solution exists or not. If that optimal solution exists, then you can just compare the corner points and you can find the optimal solution. If the optimal solution does not exist, then you can declare that there is no optimal solution and you can just stop. Okay. So this is an algorithm of solving LP using graphical method. Note that in 3 and 4.1, so in 3 and 4.1, it's possible to identify more than one optimal solution. So in this case, when the feasible region is bounded, you can have more than one optimal solution, as well as in the case when the feasible region is unbounded but optimal solution exists. Then all the points in the line segment connecting the two corner points are optimal. Okay. So this is a special case of multiple optimal solution. Is it clear? The algorithm is clear. We will use this algorithm subsequently when we are seeing simplex algorithm. So is this algorithm clear? How are we finding the optimal solution for a two variable LP using graphical method? Any questions? Okay. So I suppose there is no question. All right. So I cannot see the chat. Just let me see if there's any question in the chat. Do something.
There is some white noise, background noise.
Okay. Just a minute. Is it better?
When you speak, it suppresses the white noise. But if there is a source,
is it better now?
yes, it is. Yes.
Okay. Okay. Thank you.
Thank you.
All right. So we are in two-dimensional LP. Now we'll move to higher dimensional LP. So this algorithm is only possible to be it is only applicable to a two-dimensional LP. Now we'll see how to modify this algorithm, or what we have to do when we go to higher dimensions, because this algorithm is not possible to apply in higher dimensions. So first we have to understand what a corner point represents in higher dimensions. So when we have n-dimensional region, so what is a corner point in that region? I will not go into the details of this because it requires some other theory and we don't have a lot of time. I have given some slides. You can go through it and we can discuss once we meet. Okay. The second is, how are we sure that a corner point is optimal in an LP? So we just saw using this. So in the two-dimensional LP, we just observed that it is optimal, but is there any way to prove that the corner point is actually optimal in an LP? So we'll see those theorems which establishes the corner point is optimal. Actually, the corner point is optimal. The last question we have to ask is, how are we going to identify these points once we go to higher dimension? So in 2 dimension, we are identifying just by looking, or we are just evaluating it using system of linear equations. We are solving it and we are identifying the corner points. So what is the way of identifying corner points when we go to higher dimensions? Okay, so these are the questions we will see. So the first question is, what does corner point represents in higher dimension? I'll skip this portion. I have slides. You can just go through it, but it is known as extreme points. Okay, of what? So we will see of what. Okay, just a minute. So in 2 dimensions, any constraint is represents a straight line. In 3 dimension, that constraint will become a plane. In n dimension, that constraint is actually a hyperplane. It is of the form ax is equals to b, where you can write it as a1 x1 plus a2 x2 plus an xn is equals to b. Okay, so this is a hyperplane in n dimension. Okay, this hyperplane divides the region into 2 spaces, which is known as half space. So suppose in a 2 dimensional LP, I have a constraint like this. This constraint divides this region into 2 portions, this side and this side. So these regions are known as half spaces. So this is in n dimension. So n can be 2 as well. So this is one half space and this is the other half space. Okay. What is a polyhedron? The intersection of multiple half spaces is known as polyhedron. So suppose these are the constraints we have. So this region which we get is a polyhedron. So this, just let me do it. So this is actually a polyhedron in 2 dimension. So this polyhedron is actually defined in n dimension. Okay. What is a polytope? When this polyhedron is bounded, it is known as polytope. Okay. So we have 4 definitions: hyperplane, half spaces, polyhedron, and polytope. Polyhedron can be unbounded, but polytope is the bounded polyhedron, is known as a polytope. Okay. So what is an extreme point? Extreme point is equivalent of corner point of a polyhedron. So in a polyhedron, the corner points are referred to as extreme points. That is all I will say in these slides. Okay. It can be shown that the feasible region of an LP has at least one corner points. So you can prove it that the feasible region of an LP will have at least one extreme point. So extreme point and corner point are the same thing. Okay. And the number of extreme points are finite. So you'll not have an infinite number of extreme points in a feasible region of an LP. It will always be finite. Why is this important? You see, when we design an algorithm, we'll have to know. So suppose we are using a similar kind of algorithm, which we saw for the graphical method. So in the graphical method, we told you that we have to compare the corner points, the value at the corner points. So if the corner points are infinite, we will not be able to identify all the corner points and obtain the objective function value. So this statement tells me that you will only have finite number of corner points. You will not have infinite number of corner points. Okay. Also, the extreme point plays the same role in the simplex algorithm as the corner point plays in the graphical method. So this is what I'm telling you. Is it clear? Okay. Okay, now we are moving to something else. So this is answering the first question. This question. Okay. So I have answered the first question. What does a corner point in higher dimension mean? So it is actually an extreme point. Okay. Now we'll go to the second question. How are we? So what is the second question? The second question is, how are you sure that the corner point of a feasible region of an LP is optimal? So it says that, how are you sure that the corner point will be optimal? There are no other points. So any point inside the feasible region is optimal. We are saying that the corner point is optimal. How are we sure? So we'll see some theorems for this as well. Okay. Okay. So there is a theorem which is known as representation theorem. And we are now seeing representation theorem for a polytope. What is a polytope? A polytope is a bounded polyhedron. So there is no unboundedness. It is a bounded polyhedron. Okay. So let me draw a simple polytope in a 2 dimension. Okay. So suppose this is a feasible region of an LP. Okay. This region. And we have 3 corner points, A, B, and C. Okay. These are the 3 corner points. This representation theorem of polytope says that you take any point inside the feasible region. Suppose this is the point, any point, by the way, any point. Okay. So suppose I'm taking this point. It says that you can represent this point using all the corner points of the LP. So what we can do is, it says that you can represent X using all the corner points. So we have 3 corner points here. It will be lambda1 A plus lambda2 B plus lambda3 C. But there are some conditions. What are those conditions? The condition says that lambda1 plus lambda2 plus lambda3 has to be 1, and lambda1, lambda2, lambda3 is greater than equals to 0. You can write any point inside this feasible region using the corner points of that feasible region. This is what the representation theorem of a polytope says. Is it clear? So this is what I have said. So a point P can be represented as, so this way of writing is known as a convex combination of extreme points. Okay. So this is a convex combination. This is a technical term, but it just means this. We will weight all the corner points. These weights sum to 1, and these weights are non-negative. Is it clear? Any doubt? Okay. So I suppose there is no doubt.
There's one question.
Yes. Yes.
From Tanya, which she asks, is polyhedron an intersection of finite number of half spaces, or can it be infinite number of half spaces also?
So when you are so when you are saying infinite number of half spaces, you are saying that you have infinite number of constraints in an LP. So I don't think you can have an infinite number. So you can have, but it doesn't mean anything, right? So I think I have answered your question. So there is one more hand there is up. You can just unmute yourself and ask.
Sir, so I had a doubt regarding one point you mentioned earlier. Like for a polytope, there are finite number of extreme points, right?
Yes, there are finite number of
So
extreme points.
in 2D, assume like if my feasible region is a circle, in
So
that case, do we have extreme point there?
okay. So you're saying your feasible region is a circle.
Yeah.
I'm sorry for my not correct diagram, but you see, if you have a feasible region which is a circle, the equation of that circle will be x square plus y square, not correctly, but it will be x minus a whole square plus y minus b whole square is greater than or less than equals to r square, right? Less than equals to r square. So you're saying this is your constraint. When this is your constraint, this is not an LP anymore. What I'm saying is for an LP,
Oh,
right?
yes.
Okay.
So all these conditions you are mentioned till now is only applicable for LPs. Like the
This
power should
whole
be one.
session is about LP.
Okay.
I'll
Okay, sir.
not I'll not go to integer programming as well. Everything is LP.
Okay, sir. Clear. Yeah. Thank you.
Right.
So there's another
So
question from D. Prasad, who asks, how do we split polyhedron mathematically in high dimensional space?
so you have a constraint like this of this form. It is a1 x1 plus a2 x2 plus dot 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 an xn, where n is the dimension of the space. You can just write less than equals to b. So the equation is actually equals to b. So you can just split this as less than equals to b and greater than equals to b. So you have two half spaces. Is it clear? Okay. All right. So where were we? So we can represent any point as convex combination of the extreme points. All right. And you see, this is important. Why? Because we said that extreme points, we have finite number of extreme points. So therefore, this you can write the equations like this, right? Now, since you can write a point like this, you can write all the points in the feasible region like this, right? So what I'm saying is, you can write a set S where lambdas are variables. These lambdas are variables. And the points are, so here y1, y2, yk are the extreme points. So I'm just saying lambda1, y1, lambda2, y2 plus dot 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 lambda, you can write n. So over here it's k, m lambda n yn, such that this lambda I summation is equals to 1 and all lambda I is equals to 0. This set where you are varying lambda, this set represents the feasible region. Is it clear? So any point, so these weights, if you vary, you will go to another point. You vary the weights, you will get to another point. Okay, is it clear? So your feasible region has now been converted from this to this, where this y1, y2, yk are fixed. These are the corner points of your region. Your variables have become this lambda1, lambda2, lambda n. Now what we have done, you see, what we have done. My feasible region of the LP, we have converted it in these terms, and my variables are lambda1, lambda2, and lambda k. Suppose, so what will be the objective function? The objective function will be c times x. It was this, now it will become c times lambda y. I have not written it correctly because it is in vector form, but nevertheless, it is something like this. Now suppose this times c2, this is maximum. If this is maximum, you will just plug lambda2 as 1 and all other lambdas as 0. Or suppose lambda k, y k, c k. This is the highest among all other. So you have c1 lambda 1 y1 plus c2 lambda 2 y2 plus dot 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 ck lambda k yk plus dot 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 cn lambda n yn, right? You have the objective function like this. Now suppose this is maximum. Among all other terms, this is the highest. So what we will do is we will put lambda k as 1 and all other as 0. In that case, you see this extreme point becomes optimal. Is it clear? So the consequence of this theorem says that a corner point will always be optimal. So the optimal will always occur at a corner point. That is what this consequence of this representation theorem is. The representation theorem is just saying that you can represent any point in the feasible region using a convex combination of the corner points. The consequence is that the optimal solution will be either one corner point or two corner points, and the line joining the two corner points will be optimal. Not line, over here it will be hyperplane. Is it clear? So this is just showing that a corner point will be optimal. That is it, or nothing else. Okay. So we have answered the second question. I'll come to this one. So we have answered the first question. What does a corner point represent in higher dimension? We have seen that it is an extreme point. We have not gone into the detail, but it is an extreme point. We have also answered the second question. What is the second question? How are we sure that a corner point of the feasible region of an LP is optimal? This consequence of the representation theorem is that a optimal point will always be at a corner, at one or more corner point, at one or more corner points. Is it clear? Okay, so this representation theorem is for a polytope, but this can be written for a polyhedron as well. So it says that any LP can be represented as a set of convex combination of the extreme points plus non-negative linear combination of extreme direction. So this detail I'm not going because Professor Sachin will, I think, touch upon the details of convex non-negative linear combination of extreme directions. Therefore, I'll not go into the details of this, but just understand this, that we have a similar representation theorem for unbounded region of LP. What is the consequence? The consequence is that if an LP with unbounded feasible region, so if you have an LP with unbounded feasible region, and if it has an optimal solution, then it will always be at the corner point. If it doesn't have a feasible region, then there is no question of extreme points. But if an unbounded LP has an optimal solution, it will be at the corner point or extreme point. Okay. So we have answered the second question. Any doubt? Any questions?
No questions in the chat.
Okay, thank you, sir. All right. So we have answered the second question. The third question we have is how to identify this corner point equivalent in higher dimension. So we have seen what an extreme point is. So we know what an extreme point is for a polyhedron, but how will we identify those extreme points? So that is what we will see in few slides, subsequent few slides. Okay. So how does so we will use an algorithm to solve an LP of higher dimension. We will eventually move to simplex. Nevertheless, whichever algorithm we are using, how will that algorithm identify the corner points in higher dimension? This is what we'll see now. Okay. Okay. So we will go to standard form. So any LP can be represented using standard form. So what is a standard form? The standard form of an LP, in a standard form of an LP, the constraints are of equality type. So if you have a constraint like this AX, so AI xi less than equals to B, summation of this, what you can do is you can add slack variables. So okay, so it will be AI xi plus, so S1, so in this case it will be 1 less than equals to. So suppose we have, let me write it properly. So suppose you have two constraints, A1 x1 plus A2 x2 plus dot 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 an xn is equals to B1, and the second constraint is A2 x2 plus sorry, A2, just a minute. You will have A11 x1 plus A12 x2 plus dot 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 A1n xn is less than equals to B1, A21 x1 plus A22 x2 plus dot 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 ANN n mn xn. So here will be 2n less than equals to B2. So you have two constraints in your LP. What you can do is you can add slack variables to make it equality. So in the first constraint, you can add plus S1 and this will become equality. In the second constraint, you will have S2 and it will become equality. Okay. If you have greater than equals to, so you subtract, um, uh, not subtract, you will add surplus variables. Okay. So it will be X1 and it will become equality. I think you know this. And similarly, for each of the constraint, you will have SI. You will add or subtract. Just a minute. This is greater than this. If you add, so it will be subtract. Okay. All right. So you can write every LP in the standard form. So I have an example over here. So this is an LP where you have two constraints and this is of less than equality type. What we are doing is, since we have two constraints, we will use two slack variables S1 and S2. In the first constraint, we will have S1 and the S2 will be 0 S2. And in the second constraint, S1 will have a coefficient of 0 and S2 will come in the second constraint as with coefficient 1. So you see, this LP has been written in the standard form. Okay, why are we writing the LP in standard form? This is because we will use the theories of uh, solving system of linear equations, and then we will see how we are proceeding to develop a algorithm to solve these equations. Now the constraints have become linear equality equations. Okay, so you don't have inequality. Since we have equations now we'll use the theories of linear system of linear equations and we will solve for the feasible region and then we will see how we are proceeding. Okay, so we have converted an LP in the standard form and the constraints are written in uh, uh, equations form, which is equality form. Okay, now we will see solving of system of equations. So in a system of equations, suppose you have n unknowns and m equations. Okay, this system will have unique solution. So if this system has unique solution, so you can have three cases. First case is unique solution. When this happens, when you solve that equation and you have exactly one solution. Okay, so that is when your system of equations can have unique solution. So in this example, you have two lines, and when you draw this line, you will see that it intersect at a point. So the solution of this equation will be the intersection point of these two lines, which is here 1, 1, and you have unique solution. So this is the case when your system of equations will have unique solution. Your system of equations may have no solution. How will that happen? So suppose you have two parallel lines. In that case, it will never intersect and you'll have no solution. You can have, suppose you have three constraints or three equations here and two constraints intersect, but the third constraint is intersecting some other point. So you will not be able to solve and obtain a solution. So in that case, your system of equations has no solution. Okay. The third case is you may have infinite number of solution. So I have given one example. So this is a line. So suppose this is your graph and you draw this line like this, you see any point in this line satisfies this line. So you can have infinite number of solutions. Okay. So 5, 0, 0, 5, 5 by 2, 5 by 2, and any point outside as well. So negative points are also solutions now because you have just one equation. So this point is also a solution. This point is also a solution. This point is also a solution. You have infinite many solutions. For multiple constraints, so what you're having is, so for multiple equations, in this case, you have 3 unknowns, but 2 equations. And again, when you solve this, you will see that there are many points which satisfy these two equations, and therefore you have infinite number of solutions for these two, for this system of equations. So one point can be 1, 1, 0. So we are setting x3 as 0 in this case. This will be, we are setting x2 as 0 and we are solving. And this will be when we are setting x1 and 0 and then we are solving. We can set any other value as well. So for x3, we are setting 1 and then we are obtaining these 2 points. In this case, we are setting x3 as -1 and then we are getting these points. So you see there are multiple solutions to this equation, and this satisfies these constraints. Now, for linear programming, we are interested in this case when you have infinite number of solutions. Why? Because if you have unique solution, your objective function will have only one value. Why? Because your constraint is only satisfying one solution and there's nothing to optimize then. You will have only one solution and that is the best solution you can have because that satisfies the constraints you have. No solutions, we are not interested. We are only interested in the case when we have multiple solutions. Why? Because in that case, optimization comes into play. When you have multiple solutions, we have to choose what is the best solution among those possible solutions. Okay. So optimization, this everything with what we're talking about comes into play when we have infinite number of solutions. Okay. So suppose you have m unknowns and m equations and n unknowns. When the number of unknowns is greater than the number of equations, typically, not every time, typically these have infinite number of solutions. And in linear programming belongs to this case when you have infinite number of solutions. Okay, so this is what I have said. When you have one solution or no solution, there is nothing to optimize. Is it clear? Now we'll move into some other theory. Is it clear? Okay. All right. Now basic solution. So you see, you have a system of equations. You have m equations and n variables, m unknowns, m equations and n unknowns, and your number of unknowns is greater than the number of equations you have. Therefore, we are assuming that we have a case of multiple solutions or infinite number of solutions. What we'll do is we will set n minus m variables as 0. Once we do that, we'll be able to solve those equations and obtain a unique solution. You see, in this case, we had 3 unknowns and 2 equations. And once we set x3 as 0, we could obtain a unique solution 1, 1, 0. Once we once we fixed the value of x2 as 0 in this case, we obtain a unique solution x1 minus 1, x3 3, and x2 as 0. Again, once we put x1 as 0, we obtain this solution. So what is a basic solution? When you put n minus m variables as 0 and you obtain the solution of those equations after fixing the values of m minus n variables, any of the m minus m variables as 0, then that solution is known as a basic solution. So in this example, this is a basic solution, this is a basic solution, this is a basic solution. These are not basic solution. Okay. So this is the definition of basic solution. One more definition. The variables which we set as 0 are known as non-basic variables, and the remaining variables are known as basic variables. Again, you observe that there are multiple choices of non-basic variables. Okay. How many choices? So among n variables, you have m minus n choices to make. So there are actually n choose m minus n number of ways to select non-basic variables. Okay. Is it clear? Now another definition, which is known as basic feasible solution. You see, in LP, we have non-negativity constraints. Generally, we have non-negativity constraints. It is not always the case, but generally we have non-negativity constraints. In that case, this will be a feasible solution. You see x1 is positive, x2 is positive, and x3 is 0. This will be a feasible solution where x2 is positive, x3 is positive, and x1 is 0. But this is not feasible. Why? Because x1 is negative. So we have defined a new term which is known as basic feasible solution. It just says those basic solutions which are feasible, or the basic variables takes positive value. The basic variable takes positive value is known as basic feasible solution. It is abbreviated as BFS. And the maximum number of possible BFS you can have is n choose n minus m, which is also as n choose n. Is it clear? So you can have at max n choose m number of basic feasible solutions. Is it clear? Okay, I suppose it is clear. Now we'll see just one example of how to obtain basic solution and basic feasible solution. So this is the LP we have. Now I will draw the feasible region of this LP. It is very simple. You see, for the first constraint, it will be x1 by 80 plus x2 by 20 is less than equals to 1. And similarly, you can do that and you can draw the constraint. So this is the first constraint. This is the second constraint. Sorry, not this one. This is the second constraint. Okay. And you can just obtain the points. So this is 80, 0. This is 80, 0. This is 0, 30. This is 0, 20. This is 45, 0. And this you can just solve it by plugging equality, and you can just solve this and you will obtain this as 24, 14. Okay. So I've just drawn the feasible region and we'll come back to it once we see the values of feasible solution and basic feasible solution and basic solutions. Okay. So this is the feasible region for this LP. We'll come back to this slide again. Okay. So we had this LP. We transformed it into the standard form. So this is the standard form. We introduced two slack variables, S1 and S2, and these slack variables are non-negative. What you do is we have n is equals to 4 and m is equals to 2. So there are 4 choose 2, which is 6 ways of selecting two basic variables, right? So we have 6 conditions, 1, 2, 3, 4, 5, and 6. In the first case, we will select x1 and x2 as basic and s1 and s2 as non-basic, and we will put them as 0. So once you put s1 and s2 as 0, you will obtain these two equations. You solve this, you obtain this solution. Is it a basic solution? Yes, it is a basic solution. Is it basic feasible solution? You see, the basic variables are taking positive values. So yes, it is a basic feasible solution. Again, you select S1 and X1 as basic variables. You solve, you obtain a solution. Is it a basic solution? Yes. Is it a basic feasible solution? You see, there's no negative value. So it is a basic feasible solution. In this case and in this case, these are not basic feasible solution. Why? Because these values are negative. This is a basic feasible solution. This is a basic feasible solution. So for this problem, we have 6 basic solution, but we have only 4 basic feasible solution. Is it clear? Is it clear? Now we'll see these points in the, sorry. What we'll do now is we'll see these points. Where are these points in the feasible region? You see this point, 24, 14, 0, 0. It is actually this point 24, 14. 0, 0 is not here. We will understand this now. You see, for the first constraint, you have 5x1 plus 20x2 plus s1 is equals to 400. If this value, or if s1 is 0, you have this constraint, right? When s1 is 0. When this is less than, so when 5x1 plus 20x2 is less than 400, this is this region. This is this region, right? So in that case, S1 is taking positive value. Okay. So you see this point now. Sorry. You see this point now. This point over here, this point S1 will take 0 value, and similarly S2 will also take 0 value. Why? Because it is lying on that constraint, this line, right? So this is the same point, 24, 14, 0, 0 is this point. For this point, if you go 45, 0, 175, 0, so 45, 0 is this one, 45, 0. And what is the other value? 175 and 0. You see, we have 45, 0, 175 and 0. You see, this is the second constraint. And what we have understood till now is for the second constraint, S2 will be 0. You see, S2 is 0. S1 will be 0 on this line, but inside this region, S1 will become positive, and you see S1 is becoming positive. So this is that point. Okay. This is that point. What is this point? 80, 0, 0 and minus 350. So what is this point? 80, 0, 0 minus, what was minus 350? You see, we have x1 as 80, x2 as 0. This is the line on the first constraint, so S1 is 0. And you see, on this region, S2 was positive. On this region, S2 is negative. So you see, you're having minus 130. So this this basic solutions are actually points in the feasible region. Not all points are feasible. You see, this point is not feasible. This point is also not feasible, right? This point is not feasible. This point is not feasible. Therefore, these are not basic feasible solutions. Basic feasible solutions are those solutions which satisfy the constraints. So these four are these 4 points. These 4 points. This one, this one, this one, and this one. Any doubt? Any doubt? Okay. All right. So I'll move forward. This is the fundamental theorem of LP. What it says is that a point in the feasible region of an LP is an extreme point if and only if it is a basic feasible solution of the LP problem. Simply put, it says that extreme point and basic feasible solutions are the same thing. Extreme point is equivalent to basic feasible solution. Now you see we have answered the third question. How are we going to identify corner point in higher dimension? You just convert your LP in standard form, solve the system of equations to obtain the basic feasible solution. And those basic feasible solutions you have obtained are the corner points of the feasible region. Therefore, you can identify the corner points in the feasible region by just identifying the basic feasible solution in your LP. Is it clear? Any doubt? Okay. So there are few more theorems. If there is feasible region, then there is a basic feasible solution. If the optimal solution exists, then a basic feasible solution is optimal. So these are the things we know. Why we know? Because we knew that an extreme point is optimal. Now we are saying an extreme point is same as the basic feasible solution. Therefore, a basic feasible solution is optimal if the optimal solution exists. Any questions? So what have we covered till now? We have seen graphical method. We moved to higher dimension and we saw what does a corner point represent in higher dimension. We saw that corner point being optimal is actually proven for an LP if the optimal solution exists. And we know how to identify these corner points in higher dimension. Once we have this idea, we can have an algorithm to solve linear programming problem. Very simple algorithm. This is not simplex algorithm, although I have written simplex algorithm, but we have a way of solving the LP. What is the way? You convert the LP into standard form. Okay. Now you identify all the basic feasible solution. You identify all basic feasible solution. You compare this basic feasible solution and pick that basic feasible solution which has the best objective function value. And then you are able to solve the LP. Why am I calling this a crude algorithm? Anyone? You can just unmute yourself. So what do you see? What does this algorithm lacks? Although I have written it here, Do you understand this algorithm? You see, this is very similar to the graphical method. We were identifying the corner points, we were evaluating the objective function value at the corner points, and we were picking the best objective function value at whichever corner point we had. We are doing the same thing. We know that corner points are same as basic feasible solution. We identify all the basic feasible solution, obtain the objective function value, and pick the best. So I'm asking, is this algorithm sufficient, or is there any issue with this algorithm? Okay, so if you don't want to answer, let me answer it. First of all, you see, it depends on the fact that a corner point is optimal. But you see, when you have an unbounded feasible region and the optimal solution does not exist, you'll not be able to identify you'll not be able to identify that this is a case when no optimal solution exists. Okay. So it is unable to detect unbounded optimal solution. The second problem with this algorithm is that it is very time consuming. You are evaluating all possible basic solution and then evaluating the basic feasible solution. N choose M. If your N is large, then this N choose M will become exponential, not exponentially, it will be very, very large. So this is not a very good algorithm. Is it clear? So we'll see how Simplex refines this. Any doubt, any questions? Okay, so refining this crude algorithm. By the way, are you able to understand this, or is it difficult? Is it clear?
There's one question in the chat that
Yes.
asks, are the extreme points here are also the points in the extended form?
Extended form. I am not sure what extended form is. Can anyone help? What is an extended form?
Vikas Shukla, you can unmute yourself and ask your question also.
You said that this is a basic feasible solution, but you added here a slack variable, right?
Yeah, this is
So
a
the
standard form, right?
yeah, so the corner point in this case is in like after adding the slack variables, right?
Right.
It's not the corner point if you only consider x1, x2.
No, so you see, I think you have not understood it clearly. So for this two-dimensional LP, we saw that this is the feasible region. This is the feasible region, right? And using graphical method, you will obtain this point, 45, 0, 0, 0, 0, 20, and 24, 14. And when you evaluate this, the objective function value at this point, this will be same as for this basic feasible solution. Why? Because the slack variables or surplus variables, they take 0 coefficient in the objective function value. So these points are actually the corner points of the feasible region. Although we are adding the slack and surplus variable to solve for basic feasible solutions, these are actually obtaining the corner points of the actual feasible region. Any doubt?
Yeah, got it. Yeah, got it.
Okay. All right. So I'll move forward, refining this algorithm. So what we'll do is we will identify a basic feasible solution. We'll start with one basic feasible solution. We'll not list down all basic feasible solutions. We'll just identify one basic feasible solution, and we will refer this as starting BFS. If no BFS can be identified, then we declare that LP to be infeasible and stop. So if we're not able to identify any basic feasible solution, we will stop. Okay. So we'll stop. Now we have identified a basic feasible solution. Now we will check whether this basic feasible solution is optimal or not. You see, I'm not giving you the detail. I'm just giving you how are we going to refine this algorithm. So these are ideas. What are the ideas? Let me just identify one basic feasible solution. If I'm not able to identify any basic feasible solution, let me say that the LP is infeasible. Once we have identified one basic feasible solution, we will somehow check if this basic feasible solution is optimal or not. If this is optimal, then we will say that this is optimal and we will stop. If this is not optimal, so there has to be some check. Okay. If this is not optimal, then what we'll do is we'll move to a new and a better basic feasible solution. Some new and better. So we will moving to a next basic feasible solution, not only just any basic feasible solution, a better basic feasible solution. And then we'll go back to the step 2 and repeat. Okay. So this is some idea of circumventing this trouble of time consuming problem of this crude algorithm. We will not list down all basic feasible solution. We'll start with one basic feasible solution. We'll check if it is optimal. If it is not, then we'll move to the next and possibly better basic feasible solution, and we'll repeat the steps again. Okay. So unlike the crude algorithm, the above algorithm need not search through all basic solutions and therefore is faster. Also, it can detect unbounded optimal solution. We will see how it detects unbounded optimal solution. So if no basic feasible solution is better, then we declare the optimal solution. Then we declare that no optimal solution. But then we declare that is an unbounded case. Okay. So what we are saying is that we have a way of identifying a better basic feasible solution. If we are not able to find a better basic feasible solution, then we'll declare that LP to be optimal. So this is the idea of simplex. Okay. So this algorithm can detect unbounded optimal solution. But there are few questions we have left out. How are we going to identify the starting basic feasible solution? We have just said identify a basic feasible solution. How will we do that? What is the check of optimality? How will we go to a new and better basic feasible solution? So these are some questions which simplex answers and then solves the problem. Some related question to one. If our method fails to identify one BFS, how can we be sure that there is no feasible solution? So we are saying that if I cannot identify a basic feasible solution, let me say that the LP is infeasible. Will it hold in all the cases? Is it true? A second question related to question C is, if our method fails to identify a new and better basic feasible solution, how are we sure that we have no optimal solutions? So these are the details of simplex. We will not go into the details. Why I have mentioned it here is that this is an approach of developing an algorithm. You see, we had an algorithm for graphical method. We tried to translate those ideas to higher dimensions. Once we translated those ideas to higher dimensions, then we defined a way of solving the higher dimensional LP using some idea of graphical method. Then we saw that it had limitations. Then we tried to improve that crude algorithm with some ideas. And these ideas has some questions. What are those questions? How will we identify the first basic feasible solutions? How will we perform the check if that basic feasible solution is optimal or not? How are we going to identify a new and better basic feasible solutions? So once you have answered these questions, then you will be able to propose an algorithm which solves an LP, and that algorithm is simplex algorithm. So we'll not go into the details because this will take at least 5-6 lectures to cover everything. But these are the questions which were answered before this simplex algorithm was developed. So once we had these answers, then we could say that simplex algorithm could solve LP to optimality. It is not a heuristic. It is not giving me a solution which may not be optimal, or in some cases it is optimal, or we don't know that. It says that simplex algorithm gives you an optimal solution. How is it saying that? Because it has answered all these questions. Okay. So we will not go into the details any further. We'll just see how simplex work in a example problem. Any questions? And I think what I'm going to cover now, Professor Yogesh, which I'll also cover slightly in his lecture, but I will at least show you one example of simplex algorithm in one example LP. Is it clear? Okay. So I have 25 minutes. I'll cover in that time. So this is an example of maximization problem. We have the objective as 60x1 plus 30x2 plus 20x3. You see, I have written this as an equation, and I have defined a variable z is equals to this. So this is an equation now, subject to 3 constraints. You see, you have 3 variables, 4 constraints, and you have 3 variables. Since this is a 3 variable LP, you will not be able to do graphical method over here. Okay. We will introduce slack variable and convert it into standard form. So all the slack variables has coefficient of 0 in the objective function, and this S1 has a coefficient of 1 and all other 0, S2 as 1 in the second constraint and all other 0, and so on and so forth. Okay. Now we have 3 plus 3, 6 variables. So n is equals to 6, and we have m is equals to 4. We have 4 equations as constraints and 6 variables. You see the objective function is also written as a equation. Now you have actually 5 equations. You have 5 equations, and you could use the ideas of whatever we have talked about, and we can solve for the variables, and then we will see how we are doing it. Okay. Before that, one small definition: canonical form of a system of equations in LP. You see, we have 4 equations. The constraints. This is the first constraint, second constraint, third constraint, and fourth constraint. The canonical form of a system of equations. In canonical form of a system of equations, the basic variable appear in exactly one equation with a coefficient of 1. You see, what are we doing? We have six unknowns and 4 equations. So we have to put n minus m, which is 2. Sorry, just a minute. One, two, three. Okay, we have four. This is not 3. We have 4 slack variables. So we have S1, S2, S3, and S4. So it will be 3 plus 4, which is 7. And n minus m becomes 3. So we have to put 3 variables as 0. So these 3 variables will be non-basic. And the remaining 4 variables will be basic. Okay, so 3 variables are non-basic and 4 variables are basic. Now, if we put x1, x2, x3 as 0, our basic variables will be s1, s2, s3, and s4. Is it clear? So a canonical form is that form where the basic variable appears in exactly one equation. You see, s1 is a basic variable appearing only in the first equation and no other equation. S2 is a basic variable appearing in the second equation with a coefficient of 1. Similarly for S3 and S4. The second condition for a system of equations to be in the canonical form is that each equation has exactly one basic variable with a coefficient of 1. You see, if the first equation has only one basic variable with a coefficient of 1. Similarly, the second equation, the third equation, and the fourth equation. Okay, now why we are talking about canonical form? Why are we bringing new ideas? This is because canonical form helps us evaluate the values of basic variables very easily. You see, once we are in the canonical form, we just put the non-basic variables as 0, and the RHS gives you the value of the basic variables. Okay, so you just transform your equations into the canonical form. So suppose your basic variables are x1, x2, x3, and s1. So these are your basic variables. You transform this set of equations using elementary row operations. And then once you have done it, then your RHS will give you the value of the basic variables. That's why we are talking about canonical form. Currently, our basic variables are S1, S2, S3, and S4. Once we put these as 0, S1, X1, X2, and X3, the right-hand side will give you the value of the basic variable. So over here, the basic variables values are 48, 28, and 5. Okay. With this idea, we will proceed with the simplex method. Okay. So we have this equation. The first equation, which is the objective function, we are writing it differently. We are saying that x minus 60 x1 minus 30 x2 dot 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 is equals to 0. So this is how we are writing the first row in the simplex tabular. And these are the remaining 4 equations with slack variables written in the canonical form. Okay. So you see, I am writing this as row. So row 0, row 1, row 2, row 3, and row 4. So the first row is labeled as row 0. And these are the variables. You see, Z is a variable now. Z, x1, x2, x3, x4, sorry, S1, S2, S3, and S4. Now, in the first tabular, what we will do is we will put x1, x2, and x3 as 0. You see, in our method, we had to identify one basic feasible solution. How are we doing it? We are just taking the slack variables as the basic variables. Over here, we are just taking this as the basic variables and we are putting this as 0. Once you put this as 0 in the canonical form, this will be your solution. So our solution is 48, 20, 8, 5, and remaining 0. So this is 1 point, and this is a basic feasible solution. We have identified an initial basic feasible solution. Is it clear? All right. So this is the first tabulo. Now what we have to do is we'll have to. So once we have identified one basic feasible solution, so this LP is not infeasible. Okay. So we have done step 1. Now what we'll do is we will see if this basic feasible solution is optimal or not. So for this problem, you just see the objective function value. It is z is equals to 60x1 plus 30x2 plus 20x3. You see, increasing either x1 or x2 or x3 increases your objective function value. Therefore, this objective function value could be increased. Currently, the objective function value is 0. Z is equals to 0. Why? Because you just put the value and you will see that z is equals to 0. So you could increase the objective function value. Therefore, this solution is not optimal. So this is not optimal. Okay, now we will pick one of the variables and increase its value. So which one we pick? We can pick any one. But since we see that x1 has a largest coefficient as 60, we will pick x1. And we will label it as entering variable. We will make x1 as the entering variable. Is it clear? We will make x1 as the entering variable. This will be the entering variable. Now, you see, you have 4 basic variables, right? If you make x1 as basic variable, you will have to make one of the basic variables as non-basic. Which one will you make as non-basic? We will see how to do that. Okay. So we have decided that x1 will be my new basic variable. We will move x1 into the I have not told you this term. We will move x1 in the basis. What is the basis? The set of the basic variables are known as basis. Okay. So we will see the first equation. By the way, always remember this xi and si are greater than equals to 0. These are non-negative. Okay. We will see the first equation. What we have is 8x1. These are always 0. So we will not write this. And we have s1 is equals to 48. You can write s1 is equals to 48 minus 8x1. You see, we want to increase x1. But how much we can increase? We can increase it to that much such that s1 satisfies inequality. S1 should be non-negative. So how much can you increase this? You can increase this as 48 minus 8x1 should be greater than equals to 0. You cannot increase it further. Increase x1 further. So this way you can identify the value of x1 you can have for the first equation. What it will be? It will be less than equals to 48 by 8, which is 6. So to satisfy the first equation and satisfy that S1 is non-negative, x1 can take at max 6. You do the similar thing for the second equation. 4x1 plus s2 is equals to 20. And 20 minus, so this will be 20 minus 4x1 has to be greater than equals to 0. That is x1 is less than equals to 5. So for the first equation, x1 has to be less than, for this x1 has to be less than equals to 6. For the second equation, x1 has to be less than 5. For the third equation, 2x1 plus s3 is equals to 8. This will give you 8 minus 2x1 has to be greater than equals to 0, or x1 is less than equals to 4. So for the third equation, x1 is less than equals to 4. And for the fourth equation, you don't have x1, so x1 can take any value as large as you can. So x1 is actually less than equals to infinity, which we do not write. Okay. So the third case we do not, fourth case we do not write. You see, x1 has to satisfy all these 3 cases. Which value will satisfy all the 3 cases? X1 less than equals to 4 will satisfy this case, and this case. Okay, so x1 can take any value. It can take 1, 2, 2.5, anything. What value will we give it? We will give it the highest value. We will see how it is taking. So we will take this as the governing equation for x1 to not violate the non-negativity restriction. In that case, you see, if x1 takes 4, you see s3 will become 0. So s3 will be the leaving variable. Is it clear? We have identified the entering variable as x1 and s3 will become the leaving variable. So this is what I have written. Yes, we have identified the uh, entering variable and we have identified the leaving variable. So x1 is the entering variable and s3 is the leaving variable. Any doubt? If you don't have any doubt, then we'll move to the second tableau. What we have done, we had the first tableau, we had the values, we checked if it is optimal or not. We saw that we could increase x1, x2, x3, any variable, and the objective function value will increase, and this is a maximization problem. We picked an entering variable, which is x1. We checked all the four equations, and we saw that this row 3 is the critical row, a pivot row, and then x3 became the leaving variable. Is it clear? Up to this point, is it clear? Please respond. I don't have a lot of time. Okay, I suppose it is clear. Now what we will do, we will again make this in the canonical form. What are my basic variables now for the table, second table? It is x1, s1, s2, and s4. So we will make it into the canonical form. How will we make it? We will perform elementary row operations. So in this row, for x1 to become for this equation to become in the canonical form, the coefficient of x1 must be 1. So what we will do is r3 dashed will become r3 by 2. So this is the new r3 dashed. You perform this operation in this row 3. For row 0, it will become row 0 plus 60 times row 3 dashed. So you have row 3 dashed. What is row 3 dashed? This is row 3 dashed. We have multiplied the row by half. Now this row, once you multiply it by 60 and add it to the row 0, the coefficient of x1 will become 0. Similarly, for row 1 dashed, it will be row 1 plus 8 times row 3 dashed. And you perform the row operations for all the rows and you transform it into a canonical form. You see, this is in a canonical form. The first row has one basic variable with a coefficient of 1. The second row has one basic variable with a coefficient of 1. The third row has a basic variable with a coefficient of 1. And the fourth row has a basic variable with a coefficient of 1. And each row has exactly one basic variable. Now we have understood that once we have canonical form, you just take the right hand side and that will be the value of the basic variable. So S1 is 16, S2 is 4, X1 as 4, and S4 as 5. And the objective function value Z has become 240. You see, you have moved to a new basic feasible solution. We will just go back to that crude algorithm again. Right? We identified a basic feasible solution in table 1. Therefore, it was not infeasible. We checked if it was optimal or not. It was not optimal. So we identified a new basic feasible solution and a better one. How is it better? You see, the objective function value increased. It went up from 0 to 240. Right? So this is a new basic feasible solution and a better one. All right. And one more thing, since these are basic feasible solution, we are moving from one corner point to the other. So although this is not a two-dimensional LP, for a two-dimensional LP, we will move from one corner point to the other. So this is how Simplex will move. Okay, so it identifies one basic feasible solution, move to the neighbor basic feasible solution with a better objective function value, and so on and so forth. Okay. So we have table 2. Now we will again see if this is optimal. We will write the row 0 again. Z is equals to 240 minus 115 x2 plus 5 x3 minus 30 x3 s3. You see, If you increase x3, the objective function value will increase again. Therefore, x3 will be the entering variable now. And then we have identified the entering variable. Now what we will do is we will check for each of the 4 rows and we will see which is the exiting variable or leaving variable. Okay, the way we did earlier. We will, in this case, we will see that S2 is the leaving variable. In this case, we will see that S2 is the leaving variable. So X3 is the entering variable and S2 is the leaving variable. So the new basis will be S1, S1, X1, X3 and S4. So this will be the new basic variable set. Okay. You again perform the row operations. So in this, you again perform the row operation. What you will do is for row 2. So this is the second tableau, where the objective function value was 240. For the second tableau, you have to make this coefficient as 1. So how will you do that? Row 2 dashed will be row 2 times 2. You just multiply row 2 by 2. You will make this coefficient as 1 and then perform the elementary row operations and make this coefficient as 0. Once you do that, so I have listed down the elementary row operations. You can just read when I upload the slides. Once you do that, we will have the third tableau. So we have 2 tableaus previously. This is the third tableau. And you see which are the basic variables: S2, X3, S1, and S4. These are the basic variables. You plug the non-basic variables as 0 and you will see that this is the new basic feasible solution. S1 is equals to 24, X3 is equals to 8, X1 is equals to 2, and S4 is equals to 5. Okay. And the objective function value has increased again. It was 240 and now it has become 280. Okay, so in the third tableau, we are again seeing that there is an increase in the objective function value. Now we will repeat, we will see if this solution is optimal or not. You write the row 0 again. Z is equals to 280 minus 5x2 minus 10s2 minus 10s3. You see there is no other non-basic variable. If changed, if increased, can increase the objective function value. Therefore, this solution is the optimal solution to this problem. This solution is the optimal solution to this problem. Okay. Is it clear? Was I fast? All right. So I see a question. Before that question, I'll just tell you this example over here just shows one case where one corner point is optimal and the feasible region is bounded. So there are cases when the feasible region is unbounded. There can be cases where the feasible region is unbounded and the optimal solution does not exist. There can be cases where there is no feasible region. So those examples I have not shown you, and the theories also I have not talked about. But the idea will remain the same. We will start with one basic feasible solution and we'll try to move to the next and better basic feasible solution. Okay. So with this, I have completed. And this is a reference book which you can go through once you have time and you want to read more about this topic. So I have completed. There was one hand I raised, I saw. You can just ask your questions. Any doubt? Okay. So I think you don't have any doubt. So this is my LinkedIn profile. If you want, you can just connect with me here. All right. So I have completed my portion. Yes, I can show you that. So you see row 0 is same as any other equations in this table. So this is the initial table, right? So we identified that x1 is the entering variable and s3 is the leaving variable. So this is the pivot row and this is the pivot column. So I have not talked about this term. So this column is known as the pivot column, and this row is known as the pivot row, and this is the pivot element. What you have to do is you have to make the coefficient in the pivot element as 1. So row 3 in the next table, table 2 will be divided by 2 throughout the rows, and we will make the coefficient of x1 as 1 in this row. For the other rows, even for row 0, we will perform elementary row operations to make the coefficient of x1 as 0. So for row 0 dashed, it will become row 0 plus 60 times row 3 dashed. So what is row 3 dashed? It is x1 plus 1.5 by 2 x2 plus 0.25 x3 plus 0.5 s3 is equals to 4. So this is row 3 dashed, right? You multiply this by 60 and add it to row 0. In that case, this will become 0. And you see, once you do that, you multiply this by 60, it will be 4 times 60, which is 240. And you see that will become the objective function value in the second table, 240. And you see the coefficient of x1 has become 0. So what you're doing, you're just doing elementary row operations. So for row 0, you just did row 0 plus 60 times row 3 dashed, and you made the coefficient of x1 in that row as 0. Similarly, for row 1, you will do, row 2 you will do, and row 4 you will do. Once you do that, you have the next table. After just doing the elementary row operations, for all the rows, you will have the next table. Is it clear? Whoever was asking that question? Okay. All right. And you can call me just Shubham. No need to call me sir. So I suppose we have come to the end of this lecture or this session.
There was one question related to how to find the initial feasible solution. Initial basic feasible solution.
Okay. So you see there is some theory over here coming from linear algebra. So I'll not go into that theory. But what are we doing here is that we have transformed the LP to standard form. Once we have standard form, we will make the slack variables as the basic variables for this case. For some other case, you may have extra variables. I'm not going into that detail. Once you make those variables as basic variables, you will see that that will become your first basis. You have 4 equations, you have 4 basic variables. The other will become non-basic. And in that case, you have identified a basic feasible solutions. Suppose in some LP, you have a coefficient of minus S1. So suppose you have this equation like this. So suppose the first equation is not like this, it is like this: x1 plus 6x2 plus 1x3 minus s1 is equals to 48. Instead of plus, you had minus. In that case, you will not be able to make s1 as basic variable. Why? Because the value of s1 will be minus 48, and this will not be a basic feasible solution. In that case, you may have to introduce extra variables. Those variables are known as artificial variables. Those are more details of simplex. I'm not going into detail, but this is a way of identifying the first basic feasible solution and initiate simplex. So you need to have a basic feasible solution to initiate simplex.
One final question from Sneha here. For a minimization problem, we have to convert to maximization necessarily because of the initial basic feasible solution, or there is another reason?
No, see, if your variables in the standard form are taking positive, you have basic variables, whichever you have identified the basic variables as Whichever variables you have identified as the basic variables, they are taking positive value. You have identified a basic feasible solution, whether it be a maximization problem or a minimization problem. So suppose for this problem, we didn't have a maximization objective, we had a minimization objective, and we did transformed into a standard form. You see, these basic variables, whichever we have called at basic variables, are taking positive value. Therefore, you don't have to, what was the question?
So I think that the idea is that we convert that into a standard form so that we can use our existing algorithm. This is what I answered.
Right. So you can just initiate simplex once you identify a basic feasible solution. It should be a basic feasible solution.
If there are other questions, you can type it on the chat or you can unmute yourself and ask.
I think minimization makes sense because column 0. Now you see, if this is a minimization problem for the time being, suppose this was not a maximization problem, this is a minimization problem, you will initiate simplex as is. Okay. In that case, what will happen is this is the initial table and we have a minimization problem. Only change is the minimization problem. For this problem, the initial basic feasible solution is S1 is 48, S2 is 20, S3 is 8, and S4 is 5, and all other variables are 0. Now we'll come to the objective function. We have Z is equals to 60x1 plus 30x2 plus 20x3. You see, this is a minimization problem. If you change the values of x1, x2, x3, which is currently 0, the objective function value will increase, but you want to minimize. So this is the minimum possible value of the objective function. Therefore, this is the optimal table of simplex. The initial table becomes the optimal table, and this is your solution. The optimality test will tell you whether you will have to move to the next table or not.
If there are no other questions, yeah, go ahead.
No. Thanks. That is all. Yeah. Okay.
Last call for the questions. If there are no other questions, let's thank Shubham for giving this wonderful lecture on the introduction to linear programming and the simplex method. There will be another pre-LSO session tomorrow on the duality theory by Professor Yogesh Agarwal. Hope you join us. And thank you, Shubham, for joining. And I hope to see you on campus soon. And we hope to see everyone on campus soon for LSO. Thank you, everyone.
Thank you, everyone.